We are the Play to Learn chemistry team from Purdue University's EPICS program. We will be demonstrating a flame test lab that was originally intended for use at Jefferson High School in Lafayette, Indiana. The first thing we need to address for this lab is safety. It is very important that we remain safe for the duration of the lab time. Remember to wear splash goggles and gloves at all times. When testing the solution, spray the solution near the middle of the flame, not at the base of the Bunsen burner. In addition, only spray the solution into the flame. Some solutions are toxic. Most of the chemicals you will be dealing with in the lab are detrimental to skin and respiratory systems. Just remember to spray the liquid directly into the flame. What is a flame test? A flame test is used to detect certain metals in aqueous solutions. When carrying out this lab, you will be determining multiple unknowns using this process. Now we will get a more detailed look at how the compounds display light. We all know that a compound is made of different molecules. More so, a molecule is made of different atoms. An atom is made of a positively charged nucleus and negatively charged electrons. Looking at the diagram in the slide, we are showing a sodium atom's electron configuration. Sodium is from the first column in the periodic table, so it has one valence electron in its outer electron orbital. This one electron is relatively active compared to the other electrons because it is the furthest electron in the electron cloud. When we are spraying the solutions onto the flame in this case, this one electron will jump to another higher energy level. This is what is known as the excited state. Staying at a high energy level is not favored for the electron because it is unstable. Therefore, the excited electron will immediately jump back to the original state, which is called the ground state. In order to conserve the total energy, a bundle of photons containing a certain amount of energy is emitted. Now, let's look over the whole process again. We can categorize the process into three phases. The first one is excitation. The electron from the ground state absorbs energy and then jumps to the excited state. The second is called de-excitation. The electron likes to stay at a low energy level, so it will immediately drop back down to the lower energy state. The third phase is called light emission. In order to conserve the total energy, a photon is emitted when electrons come back to the lower energy state. The cumulative result is that an atom of a particular element will only have light emissions of certain frequencies, and this will give us different colors. Generally, small energy gaps will emit light with low frequencies, such as a red light. Large energy gaps will emit light with high frequencies, such as blue lights. Here is the overview of the spectrum. From the left to the right, we have increasing frequencies, which also means an increase in energy. The wavelength is inversely proportional to the frequency, which means higher frequencies would have shorter wavelengths. As you can see here, the red light, which has the lowest frequency in the visible light region, has the longest wavelength. The blue light, which has the highest frequency, has the shortest. Now to the actual lab procedure. Step 1. The first thing that needs to be done before carrying out the lab is to put on some type of eye protection gear, preferably goggles and gloves. Step 2. Mix 0.6 grams of NaCl or sodium chloride in 100 milliliters of deionized water. Step 3. Find the molarity of the NaCl solution that was previously made. Step 4. Obtain one spray bottle per group of prepared unknown solution. Step 5. Light the Bunsen burner, paying careful attention not to burn yourself. Step 6. Spray the unknown solution into the flame. Keep in mind not to spray the base of the Bunsen burner. Step 7. Observe and record the color of the flame. Step 8. Identify the unknown solutions by comparing the color of the flame to the handout sheet that was provided in class. So where exactly would you see the colors that are produced in the flame test? Fireworks. As mentioned earlier, when energy is added to the metal ions in the compound, the electrons become excited. When the electrons are excited, they jump back to their ground state and give off the photons, which are displayed by the colors that we see. In fireworks, these same metal ions are used and they are mixed with gunpowder, so that when the fireworks are ignited, the gunpowder gives the ions the energy they need to give off the lights we see every 4th of July. In this particular lab, we will only need to convert from moles to grams or vice versa. We will also need to know the molarity equation for some of the calculations performed in lab. The molarity equation is molarity equals moles of solute divided by liters of solution. To convert from grams to moles, we need to know the molecular mass of the metallic salts, which can be found on the periodic table. We will now be doing a sample problem to help you better understand the concepts mentioned in lab. In this sample problem, you are told to find the grams of NaOH, or sodium hydroxide, that would be needed to make a solution that has a molarity of 0.5 dissolved in 0.0005 liters of water. The first step is to plug these values into the molarity equation. We get 0.5 moles per liter equals number of moles divided by the 0.0005 liters of water. This gives us a value of 0.0025 moles of NaOH. We now need to find the number of grams this is equal to. We do this by finding the molecular mass of NaOH. If you look at a periodic table, you'll find that sodium, or Na, has a mass of 22.99 grams. Oxygen, or O, has a mass of 16, and hydrogen, H, has a mass of 1.008 grams. Because we only use one of these atoms, we just add them together to get a total of 39.99 grams. We then take the number of moles and multiply it by the number of grams. The units should cancel, leaving you with the number of grams needed. If we plug in that number, we get 0.099 grams of NaOH.
This is sodium chloride. As you can see, the color that it produces is orange. This is lithium chloride, and as you can see, the color is red.